Okay, I had muted. Okay, so let's start from problems based on alternators. This is the first problem of the day. Okay, fifth problem basically. So we have a two-pole alternator. We have a two-pole alternator which is three-phase in nature. The alternator is operating at 3000 RPM, having total number of slots is equal to 42 and conductors per slot is equal to 2. So we are supposed to determine the value of flux per pole in order to get a line voltage of 23 kilovolts. The distribution factor is given as 0.952 and the pitch factor is given as 0.956. All right. So this being the problem statement, you are supposed to find the flux per pole value. All right. So in order to solve this problem, you have to start with the line voltage value. So line voltage is given as 23 kilovolts. All right. Now, EMF equation is derived on the basis of per phase basis, right? EMF equation is derived on per phase basis. So E phase is equal to E is equal to 2.22 kp kd f phi z phase. Okay, so this is our EMF equation. Now we have been given with not the phase voltage, we have been given with the line voltage, but they haven't mentioned anything about the alternator connection. All right, but whether they mention or not, the alternator which is used in power plant is always star connected. Is always star connected. Since the alternator stator is star connected, you can find E phase is equal to E line divided by root 3. That is 23 kilovolt divided by root 3. So that will give you the phase voltage. Okay. So it is not 23 kilovolt, it is 2.3 kilovolt. All right. Sorry, it is 2.3 kilovolt. Please make a change. It is 2.3 kilovolt. So 2.3 kilovolt divided by root 3 will give you 1.327 kilovolt. Okay, please check. Okay, check whether you are getting E phase as 1.327 kilovolt. You are getting right?
Yes, sir.
Okay, fine. So phase voltage you have found. Now you can check in your problem about the given values. So E phase is known. Okay, 2.22 is a constant. KPKD is also known. F we don't know at this juncture, so you can find the value of S. Sorry, yeah. Similarly, Z phase also you can find out. So only the unknown is the flux. So that needs to be found, the unknown value of flux. All right. So let's see how to find out flux. You have to basically rearrange the equation. That's all. So before that, let us find the frequency. So frequency F is equal to Pn by 120, and that is P is equal to 2, and N is equal to 3000. You can fetch this data from the problem description divided by 120.
50 hertz.
Yes, 50 hertz. So F value we have found 50 hertz. Next you can find out Z phase. Okay. So I think I have given the detailed formula to determine Z phase. So first you find out Z total. Okay. So Z total can be found from this particular formula. Okay. I'll just put a link, provide a link. So Z total is equal to conductors. So and conductors is equal to 2 times slots. So 2 into slots. That is 2 into, okay. How many slots? 42 slots. So 84. Z total is 84, and therefore Z phase is equal to Z total divided by 3. So 84 by 3, 28. 28. Okay. So that's your Z phase. So Z phase is also found. Now you can rearrange the EMF equation to get the value of phi. So what do you get when you rearrange the equation? So when we rearrange the above equation, you can write phi is equal to E divided by 2.22 Kp Kd F into Z phase, or phi is equal to E. How much did we get E as? 1.327, right? 1.327 into 10 to the power 3 divided by 2.22 into Kp, okay, 0.956 into Kd, 0.952 into F, 50 into Z phase, 24. So when you substitute, what do you get? Can you check how much you will get? The flux per pole value as
0.46.
Webers. Correct, 0.4. For accuracy, you can maintain at least 2 or 3 digits after the decimal point. So that will give you the most accurate value. So 0.4694 Webers. So this was a slightly different problem from the rest of the lot, which we solved the other day, right? So this is what we were supposed to find, and this is the value of flux. All right. So that's your problem number 5 in alternatives. Okay. Just looking for different problems. Okay, next problem, let's take down. A 3-phase 6-pole star connected alternator or three phase 6 pole star connected alternator revolves at 1000 rpm. The stator has 90 slots and 8 conductors per slot. Conductors per slot is 8. The flux per pole is 0.05. Webers. Calculate calculate the voltage generated. Calculate the voltage generated by the machine. Calculate the voltage generated by the machine if 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 the winding if the winding if the winding is full pitched, if the winding is full pitched, winding is full pitched. Okay, fine. So this is the problem. You can think of solving the problem. Okay. So you have been asked to find the value of induced EMF, right? So straightforward formula you have to consider. Now you know about full pitched winding, right? So given Kp is equal to 1, that's because you have been asked to consider a full pitched winding. So you can just write full pitched. Yeah. But we do not know Kd. So Kd is not given. Hence, you need to determine the Kd value. Please don't assume it as 1. Kd value can always be found with the given data. So Kd is equal to, you can write on the formula, sine n alpha by 2 divided by n into sine alpha by 2, where alpha is equal to 180 divided by 3n and n is equal to number of slots per pole per phase. Number of slots per pole per phase. So let's find out n first. So number of slots, it's given 90 divided by pole 6 and phase 3. So basically 90 into 6 into 3. So 5. So n is equal to 5. So therefore alpha is equal to 180 divided by 3 into n, and n is 5. 12, right? 12 decay. So that's your alpha. So having known the alpha value, you can find out the KD value. Okay, so here I write alpha is found as 12 degree and n is equal to 5 we have found. So let me erase this and just substitute. So KD is equal to sine n alpha. So 5 into 12 divided by 2 into n into sine alpha by 2. So 5 into sine of 12 by 2. Okay. So tell me how much you'll get. So basically this is 6.
0.957.
Yeah. Since you already found 0.956. 0.9566. And you may take 3 digits after the decimal point, or more than that also you can take. Fine. So that's about KD. Okay, and then you can find out frequency. F is equal to Pn by 120, or P is 6, speed of operation is 1000 divided by 120. So 50 hertz you will get. Right. Goes 20 times and 50 hertz. So frequency is 50 hertz. Okay. So Kp is found, Kp is known, Kd is found, frequency is also found. Now you have to find the Z phase value. Z phase is equal to Z total divided by 3, and Z total is equal to 8 into slots divided by 3, or 8 into slots are 90 divided by 3. So Z phase is equal to 240. So now you can find out E or E phase, that's 2.22 into Kp is 1, Kd is 0.9566 into frequency into the flux value, which is 0.05, into Z phase, that's 240. So E is equal to 1278.72. One two seven eight 0.72. Okay, fine. So that's your induced EMF. All right. I'll give one more problem. Fine. Next problem you take down. Seventh one. A 6-pole, 3-phase, star-connected alternator. A 6-pole, 3-phase, star-connected alternator has 12 slots per pole and 4 conductors per slot. has 12 slots per pole and 4 conductors per slot. The winding is 11 by 12 full pitched. The winding is 11 by 12 full pitched. Full stop. A flux of 25 milliweber is sinusoidally distributed along the air gap. Along the air gap. A flux of 25 milliweber is sinusoidally distributed along the air gap. Determine the line EMF. Determine the line EMF. It is similar to the problem which I had solved in the previous class. Okay, data is slightly different. Okay, try solving this and come up with the answers. You're able to solve? Okay, so what you have to understand over here is that the coil is not full pitched, it is fractional pitch or short pitch because the ratio is 11 by 12, right? If you were to have a ratio of 12 by 12, then you would have had a displacement angle of 180 degree, right? You see here, 12 by 12 corresponds to 180 degree, all right? So if this is 180 degree, what happens? if you go for a short pitched winding. So in case of short pitched winding, the given data is 11 by 12. 11 by 12. So 12 by 12 corresponds to 180 degrees. So this 11 by 12 corresponds to what? The cross multiplication. So 180 into 11 divided by 12. Okay. It's about 165 degrees. Therefore, chording angle beta is equal to 180 degree minus angle of 11 by 12. So that's 180 degree minus angle of 11 by 12, that is 165. So 180 minus 165 is 15 degree. So that's your beta. So once beta is known, you can find out Kp. Kp is equal to cos of beta by 2. So cos of 15 by 2 is 0.9914. Very close to unity, you can say, right? So pitch factor is 0.9914. You can say that pitch factor is very close to unity. Done. So that's about your Kp. Okay. Once you know Kp, you can find out Kd. So Kd pretty straightforward. You have to just go with the formula, that's all. So Kd is equal to sine n alpha by 2 divided by n into sine alpha by 2. And n is equal to slots per pole per phase. So slots per pole per phase. So n is equal to slots. So slots per pole is given, right? So you can directly take this ratio. Slots per pole, that's 12. Okay. Divided by phase, it's a 3-phase machine divided by 3. So n is equal to 4. Okay. And once you know n, you can find out alpha. Alpha is 180 divided by 3n. So 180 divided by 3 into 4. So that will give you the alpha value. So 15 degrees. And now you can find out K. Sine 4 into 15 divided by 2 divided by 4 into sine 15 by 2. So when you substitute, you will get Kd as 0.9576. Kd as 0.9576. So once you have this Kd value, you can directly find the induced EMF, right? So first let us find frequency. Pn by 120. So P is 6. Okay. And N value. Okay, they have given directly the frequency value. 6-pole 3-phase star connected 50 Hertz alternator. So they have also given the frequency 50 hertz. So given frequency equal to 50 hertz. So all what you have to find is Z phase. So Z phase is Z total divided by 3, or Z total is equal to 4 into slots. 4 into slots. And what are slots? Slots are nothing but 12 times 4. So 12 into poles. Poles are 6 divided by 3. So basically it is 24 into 4. 96. So Z phase is 96. So everything you have obtained, so you can just substitute all these values in the above equation to get E. So E is equal to 2.22 into Kp. Kp we got it as 0.99, which is very close to unity, and Kd is 0.9576 into frequency 50 into flux 25 milliwebers into Z phase, which is 96. So that will give you E phase or E. Once you know E phase, you can find out the line voltage because alternator is star connected. So root 3 into phase voltage will give you the line voltage value.
So 438.
Yeah. How much is it?
438.
Volts, right?
Yes.
Okay. 438 volts. No, I was waiting for your answer because in the book they have made a mistake. That's the reason. So line voltage is root 3 times phase voltage. So you can just multiply 438 with root 3. About 758.6. .63 volts.
No, sir, the value of line voltage is 438. The final
Oh,
answer.
you said line voltage is 438, is it?
Yes, sir.
Okay, okay. So phase is divided by root 3, no?
Yes.
How much you'll get phase voltage as? Just to
252.937.
215, huh?
252.937.
Okay, okay. 252.93 volts. So that's your line voltage and phase voltage. Okay. So that's it. So that is it from three-phase alternators. Okay. Okay. One small topic is left out. Okay. It's a small theory in alternator. I'll just do it in a few minutes. So the last topic we can write down advantages of rotating field over stationary field. advantages of rotating field over stationary field, or in other words, you can also say that advantages of stationary armature over rotating armature. Okay, so it can be asked in two different ways. What are the advantages of rotating field over stationary field? Or it can also be asked something like, mention the advantages of stationary armature over rotating armature. Okay. Now, if you quickly recall the construction of alternator, in case of alternator, you had seen that, let's say this is your stator. Okay. Your alternator is consisting of the three-phase conductors kept on the stator side, right? So in case of alternator, conductors are kept on stator and rotor is consisting of magnetic fields. Okay, so this is your rotor. So rotor is consisting of what? A pair of north and south pole. For representation purpose, I have taken only a pair of poles. So your rotor is nothing but a field system, and your stator is nothing but conductor or conductor system. Okay, so this particular setup you can see in case of alternator. On the other hand, the counterpart of alternator is DC generator in DC electricity. Okay, in DC generator, you will find a different setup in the sense the conductor and field system is interchanged. That means to say, on the stator, you can find the field system interchanged. Okay, so this is your stator. So what do you have in DC generator? On the stator, you will have the field system. And on the rotor, you will have the conductor. Okay, all these small circles represents conductors. Okay. So this is your rotor, and in bracket, let me write conductor. Okay. Now, okay, every now and then I used to mention about air gap, right? In problem statement, quite often you have heard of a term called air gap. Air gap is nothing but the clearance between stator and rotor. So for example, this is air gap. Air gap is nothing but what? The small clearance between stator and rotor. And why do you need that clearance? You need that clearance so that rotor can rotate free. If there is no clearance, what will happen? This rotor will ram against the stator, and you will not get any mechanical motion. And if you get any mechanical motion, that motion will be very, friction-prone motion you are going to get. Okay. So in alternator also you can show. So this is your air gap. This short gap between stator and rotor is your air gap. Of course, we are not going to talk about the air gap distribution, etc., etc. I just felt, let me show you the air gap. Okay. Now, construction of DC generator and construction of alternator. In modern days, you can see the alternator construction using this approach. We don't construct an alternator with this approach. In a sense, in your alternator, you can observe that field system is mounted onto the rotor. Hence, in an alternator, you will have a rotating field. Also, the conductor system is kept on the stator. Hence, you will have a stationary conductor. Though we know that DC machines were invented first, then why did we go for a drastic change in design? So this design was working good. This design was giving about an efficiency of, slightly more than 80%. Even your alternator gives about almost same efficiency, 80%. Though the setup was giving the same efficiency, what made the designer to go for this setup, a different setup? Okay, so that is what our point of discussion. What advantages are you going to get if you go for a rotating field over a stationary field? All right. So let us look at these advantages one by one. So the first advantage is that probably you can say it is easy to insulate. Okay, it is easy to insulate. It is easy to insulate conductor system if kept on stator. So first advantage is easy to insulate. Insulate means the insulation given to the conductors. So it will become very easy if you place the conductors onto the stator. Okay. So how to understand this particular point? Okay. So the magnitude of line voltage in case of alternator is 11 kilovolt. So alternator produces electricity at 11 kilovolt level, and typical power rating of alternator is somewhere about 50 MVA, megavolt amperes. So the level of voltage production is at 11 kilovolt, and the power handling capacity, the total power handling capacity is about 50 megavolt amperes. So you can determine the line current. So having known the line current, you can appreciate the first fact. Okay. So apparent power, yes, is equal to root 3 EL into IL, right? So that's your apparent power for a three-phase machine. So IL is equal to S divided by root 3 into EL. So let us quickly substitute. So 50 MVA, 50 into 10 to the power 6 divided by root 3 into 11 into 10 to the power 3. So this is a very typical case what I have considered of a typical power plant. All right. So it is 50 mega divided by root 3 into 11 kilo. So the current value, you will be astonished to see 2.62 kiloamperes. 2.62 kiloamperes, or in other words, you can say 2600 amperes. So imagine the magnitude of current, 2600 amperes. So this high current can produce a tremendous amount of heat. Now, in order to protect the conductors from heat, you have to go for insulation. Now, if you look at the space of a stator, you can always say that stator will have a larger place to accommodate the conductors as well as the insulation. On the other hand, rotor will have a smaller place. Place, because rotor is kept inside the machine. So inside the machine, you will have a smaller space. So this is one of the reasons why your conductors are kept on the stator side, because if you keep the conductors on the stator side, you will have larger place to accommodate the insulation to protect the alternator against high currents. All right, so this is the first advantage. Second advantage is that rotor becomes lighter if field system is kept on rotor side. Rotor becomes lighter if the field system is kept on rotor side. Now, what is the advantage of having a lighter rotor? Lighter rotor means lesser mechanical energy is required to propel the rotor. Propel means to initiate motion. Okay, so this is your rotor, right? So let's say this is your rotor. Now the rotor is connected to turbine. This is your rotor, and through shaft, the rotor is connected to turbine. If your rotor is small, obviously you can reduce the turbine size and you can initiate the motion in your rotor. On the other hand, if your rotor were to be like big or huge, then you would have required a bigger turbine, and bigger turbine requires higher power input. So what happens is that if you make your rotor size as small as possible, you will be able to rotate that particular rotor with a smaller mechanical energy. So that makes your construction cheaper. And even electricity cost becomes very, very less. That is the second advantage. And how is it possible? How to make a lighter rotor? Using point number 1. That is, if you shift all the insulator along with conductors onto the stator side, you will have a lighter rotor, because you have seen that the stator current is in the order of 2000 amperes. So to protect the conductors from 2000 amps of current, you will have to use huge amount of insulation. That insulation could be in the order of few tons, several hundreds of kgs of insulation you may have to use. Imagine if you place all the conductors along with insulation on the rotor side, what would have happened? You would have had a heavier rotor, and heavier rotor would require larger prime moving energy. So that makes your setup very, very costly. So that's the reason it is convenient to keep the conductors on the stator side rather than on the rotor side. Okay, so that's the second advantage. Okay, I'll give the notes for this. So you don't have to give all this explanation when you write it in your exam. So this explanation I'm giving for your knowledge. Okay. The third one is lesser sparking problems. Okay, so sparking problem, it is not new, right? You have seen this sparking phenomena in the transmission tower or transmission pole. Okay, sometimes you will be able to see bright light coming out of the conductors, or sometimes even in our household switches. Sometimes when you turn on or turn off a particular switch, you will be able to see the spark. So this sparking phenomenon is basically due to the loss of dielectric property of surrounding air. So the moment the air loses its dielectric property, what happens is that the ions can jump from point A to point B because there is no insulation in between. Okay, so that is about the sparking phenomenon. Okay, now in our discussion, I'm relating this sparking problem to uh, the placement of conductors onto the rotor side. If at all, if you had kept the conductors onto the rotor side, what would have happened? So conductors work at 11 kilovolt level. Conductors, the EMF gets generated in the conductor is in the order of 11 kilovolt, and nature is AC. On the other hand, field system is normally kept at 110 volt to 220 volt DC level. AC or DC, that is just the classification of electricity. But I want you to compare the magnitude of voltages. So your AC voltage is operating at 11 kilovolt level, and your field system is operating at a very, very low voltage level, which is 110 volt to 220 volt. Okay, why do you need this DC? This DC is required for establishing electromagnetism. Electromagnetism. Okay, because the field system, what you are using, is not made up of permanent magnets. It is made up of electromagnets. So electromagnets require electricity. So that is the reason why DC is injected. Okay. Now, this is at 11 kilovolt and this is at 110 volt or 220 volt. Okay, it's a very well-known fact that higher the voltage level, greater will be the sparking problem, right? So if you had mounted the conductor system onto the rotor side, what would have happened? Rotor is rotating, right? So due to friction, the sparking problem would have been, you could say worst. Okay, so that's the reason, by keeping safety as the prime reason, it is better to keep high voltage side on the stationary side and low voltage side on the rotor side. All right. So this is the third advantage. You can reduce the sparking problem. Fourth advantage. For conductor system, you need 3 slip rings and 3 brushes. On the other hand, for field system, you need 2 slip rings and 2 brushes. If you want them to keep, on rotor. So if you want to keep the conductor system onto the rotor side, you need 3 slip rings and 3 brushes. Okay, why 3 slip rings? 1 slip ring for R phase, Y phase, and B phase. On the other hand, if you want to keep the field system onto the rotor side, you would need only two slip rings. Why only two slip rings? One for positive terminal and one for negative terminal, because field system operates at DC level. So the answer is right in front of us. Greater the number of slip rings and brushes, greater will be the operating cost or maintenance cost. Okay. Now, why more maintenance cost? Because rotor is a rotating part of the machine. So rotor keeps on rotating, right? So when the rotor is under motion, what happens is that the brushes, keeps on coming in contact with the slip rings. So due to this physical motion, there can be wear and tear in the brush segments. So brush segments as well as the slip ring segments needs to be changed every now and then. So if you go for a field system on rotor side, you will have to just replace or you will have to just maintain two slip rings and two brushes. On the other hand, if you were to keep the conductor system onto the rotor side, then you will end up in maintaining how many slip rings? 3 slip rings and 3 brushes. And brushes and slip rings are very, very costly. The slip rings are made up of high-grade copper, and brushes are made up of soft carbon material. So they are very expensive. So if you keep field system onto the rotor side rather than the conductor system, you will be able to reduce the maintenance cost. Okay. So that's the fourth advantage. Lesser maintenance, you can say. Lesser maintenance. Lesser maintenance. So that's your fourth advantage. Okay. The last advantage, fifth advantage. So you know that field system is lighter because it works at lower voltage. Lighter because it works at lower voltage, 110 volt DC or 220 volt DC. On the other hand, conductor system is heavier. Okay, we have seen this particular fact in point number 1. Heavier in the sense it works on high voltage. And what's the magnitude of voltage? Typically 11 kilovolt. What would have happened if you had placed a heavier system onto the rotor side? So rotor is rotating in nature, right? So this rotor, this is your shaft, and this is your rotor. So as the rotor keeps on rotating, what happens is that if you had placed this conductor system onto the rotor side, the conductor system would have experienced large amount of or a greater centrifugal force, right? Centrifugal force, basically the force acting on circular rotating body. So due to this large centrifugal force, there will be greater mechanical stresses developed in the conductor system. And due to these mechanical stresses, what can happen is eventually the conductors may come out of the surface and can touch the stator part, which is very, very dangerous because your conductor system is working at 11 kilovolts of electricity. So keeping safety as the prime concern, it is always advisable to keep lighter and lower voltage system onto the rotating part of the machine. Lighter and a lower voltage system on what? The rotating part of the machine. So 110 volt is a lower voltage and your field system is lighter. So that's the reason, for the sake of safety to the operator as well as to protect the machine, it is always better to keep the low voltage, that is the field system, onto the rotor side. All right. So these are the 5 major advantages of keeping the field system onto the rotor side, or by keeping the conductor system onto the stator side. Okay. So that concludes today's session as well as the alternator chapter. All right. If you have any doubts, you can ask me